Welcome everyone out there. Thank you for joining today's live talk about engineering rock mechanics. Today we are going to provide you an overview of some key aspects you have to know and to consider when doing numerical simulations in engineering rock mechanics. But that's just the beginning. We named this entire series Rock Your Analysis with PLAXIS. I'm pretty sure you will rock it if you're joining us the upcoming weeks on this journey, where we would like to show you how practice can be used for your rock-related project. You see on the top right a QR code which leads you to our landing page, and you can see all upcoming blog articles and events of this entire series. So um, make sure to register, open this link. You'll see a full overview of what's coming next. So who is we? Let me introduce myself first. My name is Manuel Aufenthaler. I'm a product sales lead of geotechnical solutions with Bentley Systems, and I'm happy to have two experts here with me who are going to support me, Risha Vitas and Michael Laos. Risha, to start with a quick introduction of yourself. Uh,
I'm supposed to introduce myself. To be honest with you, Manuel, on my side, I cannot very nicely hear you. I'm not sure it is for me. Can you hear me properly, Manuel? It's okay. Sounds
we do
clear.
hear you. Yes, we
Oh,
do
okay.
hear
Okay.
you.
It's a bit better on your side now. So that was the idea for me to introduce myself, right, Manuel?
Correct, correct.
Okay. Thank you very much. So welcome everyone. My name is Richard. I am with Bentley and formerly PLAXIS, but now with Bentley for more than 13 years. And I'm working as an application engineer for Bentley, while participating to all kinds of activities, providing expert services, running in-house training courses or open enrollments or developing marketing materials. And I'm happy to be here with you today, so together with Miguel and Manuel for this LinkedIn Live.
Thank you, Risha. Michael?
Hi, I'm Michael Laoth. I'm a product manager with PLAXIS, and I'm trained as a civil engineer. And most of my background is in seaports and in offshore structures.
Great. Thank you. Thank you for your introduction. Can you hear me better now?
Yeah,
Okay, great.
much better now. Yeah.
Perfect. So as I said, um, well, this is just the beginning. So make sure to check out the upcoming rock events and blog articles to be released. Follow the QR code, and I'm sure we will see each other a few more times in the upcoming weeks. What we are covering today is basically some key aspects you have to be aware of before performing any numerical analysis. So to tailor this entire series towards your needs, uh, we run two polls during the last month and asked you about which rock-related industry and projects you mostly work in. We got quite some good feedback and some good participation. Looking at these results, Michael, is this in line with your or let's say with our current PLAXIS users working on rock-related projects, or did you expect to see something different?
I'd say they are mostly in line. I was maybe expecting even a larger share from transportation based on past events and conversations we've had. I was pleasantly surprised to see 26% in underground mining and 16% in open pit mining. So maybe it would be, if I could ask you something to those of you in mining and especially in underground mining, make a bit more noise. Talk to us, talk to Manuel, to Richard, to myself, and tell us a bit more about the projects that you're working on and the kind of challenges that you face and how can we help you.
Correct. That's
Something that
that's that, that's really that's a good point, I would say. So feel free to reach out to any of us via email or via here on LinkedIn. We're always happy to support you and bring your ideas forward.
Yeah. Also, something that surprised me is the low share of others that we have in both polls. So since LinkedIn only allows 4 elements per poll, when we created them, we were feeling all the time that we were leaving so many things out, and in the end, only 9% in one and 3% in the other. That was a bit surprising.
Okay, which other fields of projects or applications or even industries were you expecting to see?
Maybe a bit more from oil and gas, offshore geothermal, nuclear waste management, or projects like vertical drilling shafts, things that may be a bit smaller in size, but that sum together, I was expecting them to form a larger share of the audience.
Okay. Yeah, that's a valid point. But let's take these poll results as a starting point. Um, we can see that well, most geotechnical engineers working with rock do have to perform slope stability analysis or do have to analyze deep underground excavations. And before such an analysis should be performed, a lot of pre-work is basically necessary, and this pre-work is super important for each good and sound numerical analysis. Maybe Michael again, what does a geotechnical engineer have to consider before even thinking of performing a numerical analysis of such applications? What you personally see the main challenges?
I would say challenge number one is uncertainty. It's true that uncertainty is a factor in every field of engineering, even more in geotechnical, but even more in rock engineering projects. It's not that we need to manage uncertainty, we're navigating on it. So, a good start is always the geological history of the site. This will give us an idea of what to expect from what we have there, whether there have been major tectonic events and in what preferential directions, whether the stresses from those have been released or not, and also the probable composition of the rocks that we'll find. And we could find some nasty surprises there. There are some rocks that are viscous, some that are susceptible to swelling, some that dissolve in water. And I have seen constructions that have stopped because the rock was literally dissolving under them.
Oh my God,
Yeah, that was
nice
not a
surprise.
nice thing to see. And
Uh,
then we can move into the characterization. And here's when things start to getting fun. We have very good site and lab testings in for soils, but comparatively, testing in rock is much more difficult, much more expensive, and way less precise. And if you come, sorry.
No, that's right. It's I mean, in general, it does differ, let's say, from soil testing, and I think also one point is the scale effect, right? So maybe you or Risha can elaborate on that as well.
Yeah, indeed. If you come like me from other engineering specialties, your first question is how do I characterize this rock material? But when you're in rock projects, you're not dealing with the rock materials that just half the story. You're dealing with rock masses, and those have the contributions of both the rock and the many discontinuities that are there. And it's their mutual interaction what determines the behavior of the system. And to give you an example of how this manifests into scale effects, if you take a sample of rock on the field, you bring it to the lab, and you take 3 specimens of different sizes of that same rock, the smaller one will be the one that has the stronger capacity. And as you move to larger samples, that capacity will decrease. That's not nice because, yeah, if you extrapolate that to the field, then it means that what you measure in the lab will always have more strength than what you actually have in the field. And the reason is that as you're increasing in size, you're starting to mobilize more discontinuities that become relevant at larger scales.
Yeah, where if we come back, let's say, to these two specific applications, so slope stability analysis and deep underground excavation analysis, where do you basically see there, let's say, the main differences in approaching such an application when you, well, basically, um, the goal will be to perform a numerical analysis. So what's the difference there, and let's say in the approach?
Well, the first difference, the first thing to consider is the in situ stress. In slopes, it's almost fully released because you have a free surface there. And when you're excavating, you are the action that releases that stress there. And this in situ stress can be helpful, and it can increase the friction at discontinuities and help lock blocks together. But it can also be a source of hazards like stress-induced failures, like spalling and rock bursts, which are sudden and brittle.
Okay. Well, basically, well, to sum this up, there's quite a few pre-work needed and pre-knowledge needed, basically, to well, before thinking of performing a numerical analysis. So we said there's uncertainties we have to deal with. Laboratory testing is time consuming, expensive. We have to take scale effects into account. And of course, depending on the application itself, there is different stress conditions. And I would say there's way more pre-knowledge necessary. So we even need to know what the rock mass properties and its behavior is about. Um, and if we look at rock behavior does in some respects differ from soil behavior. And that's of course due to the fact that we are dealing with a natural geological material, right? It's discontinuous, it's inhomogeneous, it's anisotropic, um, inelastic, and there's numerous randomly oriented zones of initiation of potential failure. Richard, could you tell us and elaborate a little bit on the meaning of these properties and behavior of rock mass? Where do we find substantial differences, let's say, to soil properties and
Yeah,
soil behavior?
yeah. Well, indeed, here you are, Manuel, you are providing yeah, an exhaustive list of relevant aspects that might be considered during a finite element analysis or during an analytical analysis in general, I would say, not specifically finite element. Some of those characteristics are relevant to geomaterials, and some of them are even more specific to rock masses. And with that respect, I would say the first one, the fact that you may be dealing in some situation to a discontinuous media is very particular to rock. Indeed, we do have within this material sets of joints, fracture joints in could be in any directions, and along which it is expected that lower strength properties might characterize them, and this is something that needs to be addressed properly. So I think the picture here you are referring to something called the block size, and I think the block size is one important aspect first to compare with respect to the size of the structure to be constructed, or even more precisely the zone to be excavated. And depending on that, well, we might it might become essential to take into account this discontinuity per se, or eventually we could consider still an equivalent continuum approach. This is one aspect during which the upcoming campaign will focus on. The next aspect, talking about inhomogeneity and anisotropy and inelasticity, I would say. So those are not specifically just for rock. They are something which characterize geomaterials in more general aspect. It's also something which is perfectly relevant for soil.
Correct. Yeah.
So this inhomogeneity is just the fact that properties of the soil, mechanical characteristic in terms of stiffnesses, and even more importantly, in terms of strength, varies in space. So this is what it is. Anisotropy is the fact that those characteristics may be different in different direction. And it could be anisotropy in terms of stiffness, but also anisotropy in terms of strength. It might be quite characteristic. In elasticity, it's something quite generic, which is used in many fields for almost all material. While in elasticity, is referred to what we may call irreversibility, the fact that deformation after application of load might become permanent. There is no elasticity means that we have full reversibility, we have full conservation of energy. In elasticity means that some of the energy of the work of the load being applied is being lost, and usually within PLAXIS solution in elasticity is taken into account through plasticity theory. So we are considering the development of inelastic strain by plastic strain with different flavor. We could have perfectly plasticity with hardening. We could have more elaborated concept of bonding surface with kinematic hardening, etc. But inelasticity is just a way to take into account dissipation of energy and generation of irreversible strain. Let's put it that way. This is something that we have been doing for decades with soil already, and we also do for rock. The next aspect, the fact that you have randomly oriented zones and potential initiation of failure due to the fact that along those zones you may have weakest or lowest strengths, while it's specific to rock, and especially specific with considering a discontinuous modeling approach. Just the fact that you may have orientation, which could be arbitrary, and along with this orientation, you will have development of irreversible strain, elastic strain, at lower stress value than in the rock mass itself. This is what it means. Scale effects, I guess Miguel covered this aspect quite well in the previous slide. So this is something that needs to be properly accounted for. And if some laboratory test data are available regarding rock strength, consideration should be made on scale effect, and consideration of strength property for the rock mass might be lower to some extent to take scale effect into consideration. Softening and brittle material is just a way you may describe failure once you reach the peak stress. Softening relates to the fact that stress will decrease as failure further progress, and if the strain over which the softening happens is relatively limited, at some point we may talk about brittle behavior. So the brittle behavior correspond to sudden fracture of the rock mass once the peak stress has been reached. So we do have here as well specific models that take this into account, and especially consequences about what we call re-regularization techniques. As once introducing a model or a constitutive model with softening, we may have mesh-dependent results, and specific techniques needs to be used to take this into consideration and obtain mesh-independent solutions. Last one is time dependency. Last but not least, with time dependency, we could think about creep, the fact that over time, stresses that will develop due to the excavation process will relax, leading to increase of the forces onto the support system. That is one aspect. By time dependency, we can also think about swelling, which is also characteristic of rock. The fact that the rock, with time, we start developing swelling strain, the amplitude of which depends not only upon time, but also about the level of confinement, stress level being applied.
Correct.
So this is briefly presented what this would this would mean from a numerical modeling point of view.
Thank you, Risha. And I think that we recently published our first blog article written by Michael, and we do cover already a few of these well behaviors um, in that blog article. So make sure. I mean, again, you can open this QR code, and you will have an entire overview of the recently published blog articles, um, which are related to this series and all upcoming ones. Michael, do you know anything? Well, would you like to complete, or let's say to add additional points to this list which Richard hasn't touched?
It's not in this list, and it's not in the block either. But everywhere in geotechnical engineering, there is one wild card that always messes up everything, and that wild card is water. So the
That's
moment
true.
where you have water circulating in the discontinuities, yeah, things start changing. It creates pressure that contributes to open them. So it changes the friction properties of these discontinuities. And also, since most rock is either non-porous or has non-communicated pores, water can only flow through this discontinuity network. So then you can have very large volumes of water in a very short time.
Yeah. I mean, water. Even I mean, when we talk about soil, when we talk about rock, it's always the biggest enemy and a friend, maybe at the same time.
Yeah, indeed. And we were talking before about solubility, and Richard talked about swelling. The most fun comes when you mix the two and you have a material that is swelling and soluble. So you go on the site, you assess your geology as no risk of swelling, but then you've got a water current that is uh, transporting soluble minerals from upstream to your site, and suddenly your site starts swelling out of nowhere. Why?
Yeah.
Water.
Sounds like big fun, and no one would like to have these kind of surprises, let's say, in your own project. So that's correct. I would say so far we have heard and talked about the pre-work necessary to perform a numerical analysis. We now talked about some crucial properties and behavior of rock and rock masses. And now it's time to address the following topics. So let's talk about which numerical analysis approach is most suited for your specific rock related application. Um, we know and we have heard that at some scale all rock is fractured, right? So Michael, can you let our audience know about the numerical approaches we have to analyze the behavior of rock mass problems? Well, basically depending on the relative scale of these discontinuities.
Exactly. And the keyword there is relative scale. So relative to what you're trying to build. So if we focus on the very right of this picture, we have the quote unquote intact rock, and that we can treat as a continuum and use for that the properties for the rock material. We judge that any discontinuities that may be in the picture are enough removed or are not so relevant so as to condition the mechanics of our problem. If we go to the other end, to the very left, we have the rock that is so fractured everywhere that we can again consider it homogeneous. And we call this equivalent continuum because we're using the same tool, continuum homogeneous material. But here we will input the properties as the ones for the rock mass. So including the contribution of both the rock material and all of the small smeared discontinuities that exist there. What this approach doesn't allow us to model, and for what we will need to be somewhere in the middle, are the localized deformations. So the significative relative displacement that occur between phases of large discontinuities. And for that, we require perhaps the most complex engineering judgments, because we could have, as in the second picture, a mix of both larger and more significant and smaller discontinuities. So we need tools to decide which ones do matter to us, which ones have a scale enough to influence singularly the behavior of our model, and which sets of discontinuities we can consider uh, from a homogeneous equivalent perspective.
Yeah, I mean it's rather yeah well a crucial task basically to decide how ones can basically describe let's say the rock mass itself. Richard, can we, if we are using our solution, if we're using PLAXIS, cover basically each of these well pictures and well continuums and discontinuums?
I would say to a large extent, yes. So first, just for the audience here today, there exist rules of thumbs to evaluate which of the three situations here is the most relevant for your practical application. It's those rules of thumbs usually are considering the block size on one hand, the level of in situ stresses on the other end, and finally the size of the opening in the rock mass. And based on the three aspects, it helps the user to decide whether he should be using an equivalent continuum, a discontinuum, or a continuum approach. When it comes to continuum approach, it's relatively straightforward. I mean, any Hook and Brown or even more Coulomb approach could be applied, of course, in conjunction with field stress for defining the initial situation, which is quite relevant, as mentioned by Miguel. In terms of equivalent continuum, I would like to mention a specific model, especially like the jointed rock model. That could also be of relevance. And when it comes to discontinuum, where we do have currently interface element and soon discontinuity element that has been recently introduced to PLAXIS, which can deal with, to some extent, be used for the discontinuum approach. That's what I can say as a very general comment at this stage. But maybe Miguel, especially on the last aspect on discontinuum, wants to comment a bit more.
Well, perhaps it would be good to also comment on the limitations of the tool. In the end, PLAXIS is based on finite element method. And even if we're considering embedded discontinuities and their singular contribution to the mechanics of the problem, the framework in which we formulate our equations are still the framework of continuum mechanics. So we can model, let's say, up until the onset of failure. If you want to model larger displacements, if you want to model the complete detachment of blocks and the growth of new fractures, then finite element is not really the tool that you require for your job.
Yeah, so basically it's not something which is solely related to our solution, but it's the entire, well, it's basically the numerical method which is not appropriate for these kind of yeah investigations, let's say, post failure phenomena, let's say. So
well, just may add something. I'm not sure whether this is purely strictly related to a limitation of finite element, but maybe missing the most relevant feature in what we are currently offering there with that respect. I'm talking about a true contact formalism, for instance, and the consideration of very large, displacement. So this is that's what it would take. And also considering that we are working and formulating all our equation in an implicit framework, which is also for highly nonlinear problem, maybe not the most the most optimum solution. So well, this is what I wanted to add.
Highlight. Yeah, well, it's and that's necessary. We always in everything we do, we need to know what can we do and what are the limitations of a product, of a solution. So well, we've heard that discontinuities in general and naturally have an influence, right, on the mechanical behavior of the rock mass, and that their effect will vary depending on the relative scale of the discontinuities with respect to the dimensions of the mechanical problem. So fractured sometimes means that we have to reinforce or support surrounding rock masses, and that's our next discussion point, discussion item. So reinforcement and support. Richard, what's the difference between support and reinforcement, and how can they be modeled in PLAXIS, basically?
But I guess it's a very nice drawing, very nice picture, which all credits should be given to Miguel, by the way, who is doing this in his free time. So well, thank you very much, Miguel, for providing this. By support, what we are meaning by support are the means used to support the excavation area, and reinforcement are the means to reinforce the soil, so improve the strength of the soil so that they remain as a unique mass and still have the possibility to develop stress arching. In PLAXIS, as you could see here, we are talk about support. I would like to maybe I could talk about shotcrete and steel arches, which are maybe the two most relevant type of support one could think of. There are concrete as well for the final lining, but I would say shotcrete and steel arches, and which can be applied on either plate element, as you could see, the blue lines on the left-hand side figure, or as a solid, as a continuum element, which is the green volume on the right-hand side. Sorry. With respect to reinforcement, PLAXIS offers a very generic element called the embedded beam, which is perfectly suited for the modeling of rock bolts. So the embedded beams is made of a beam, as the terminology says, connected to the surrounding soil by means of non-linear coupling springs with non-linear behavior, meant to reproduce the soil-structure interaction. So those are the elements you could see in purple there. So they are well suited for rock bolts and cables as well, to a certain extent, but especially rock bolts. And next to that, we can also, in case we are considering free lengths of those elements, simply use the node-to-node anchor. So the node-to-node anchor in PLAXIS is the most simplest element one could think about. It's simply a uniform, linear, unidirectional spring, which is here represented on the right-hand side by the black line, actually, and which could be connected to an embedded beam. The embedded beam then representing the grouted length of the anchor. So this is, well, very briefly, the type of elements that we can use in PLAXIS for modeling support and reinforcement. With still ongoing development as we speak with that respect, but maybe Miguel wants to add up on that.
No, nothing additional from my side. Thank you, Richard. And you see what I do when I'm not working. I play with PLAXIS.
Well, it's even a nice task to do in your free time. So it's I would say we see and we've heard that we basically have structural elements. We do have constitutive models to take reinforcement and support into account, and I would say that's it for today. If you want to hear more about the value Plaxis can bring to your day-to-day work when dealing with rock-related projects, make sure to register for our webinars, read our blog articles, and we will see each other soon. You can use the QR code to access this landing page. Thank you for joining today. It was a pleasure. Thank you, Michael. Thank you, Reisha, for your expertise. And we will see each other soon in the next webinar. Thank you. Bye bye.
Bye
Thank
bye.
you.